Hi everyone, we're going to talk about energy of a photon, but this time we're actually going to do the math with this one. So when we talked about waves, we usually talk about amplitude being related to the energy of a wave, and that's true for mechanical waves. But when we talk about photons, we're talking about electromagnetic waves. And even though a photon, according to Einstein, can be both a particle and a wave, we're going to specifically look at the wave nature of that photon. And its energy, therefore, is more related to the frequency of the wave, not just the amplitude. Because again, the amplitude is just how many photons are hitting at a particular time. Well, to backtrack a little bit, William Herschel was the first one to discover that there was more than just visible light. We didn't know about all the different types of waves in the electromagnetic spectrum. We didn't know from radio waves to gamma rays. We could just detect what our eyes could see. Then William Herschel wanted to see what were the differences between the different colors of the rainbow. And so he passed sunlight through a prism to create the rainbow, and he would put a thermometer in each color and record the temperature that it would get to. And just as a control or experiment, he put it in front of red. And he noticed that that actually became more warm, was hotter than red itself. Violet was the coolest, and then red was the hottest, and then something before red was even hotter than red. And that eventually became known as infrared, where infra means below or beneath. And so he was the first one to determine that there was more to light than what we could see. Now, over the next 100 years, other electromagnetic waves were discovered. Actually, ultraviolet was discovered the year after by using a chemical process. And by the time Max Planck came around, he was looking at what we call black bodies. Black bodies are something that perfectly absorb energy and therefore can also perfectly emit energy. And he was looking at the emission from black bodies, like what color light, what temperature of energy was given off by each one. And he wanted to see if there was a relationship between those. And after a lot of experimentation and stuff, he actually came out with what we now today call Planck's constant. And the equation E equals hf, where this is the energy of an individual photon. Now there's two different versions of Planck's constant. I like to call them two different flavors. There's the joules version and the electron volt version. The joules version is 6.63 times 10 to the negative 34 joule seconds. Now don't really worry about the joule seconds. For the constants, we mostly put units on the end to make sure we get our answer in the units that we want them in. So 6.63 times 10 to the negative 34 joule seconds is the one if we want the energy in joules. But we notice that energy of an individual photon is really, really small, and joules was too big of a unit for energy, so we developed a new one called the electron volt. And so Planck's constant in electron volts is 4.14 times 10 to the negative 15 electron volt seconds. But just think of electron volts as like centimeters compared to joules would be like kilometers. That's not the best example, but it gives you a kind of a scale. Electron volts are really, really small amounts of energy. Joules are much larger amounts of energy. So let's get into the math. If we have a wave that has a frequency of 6 times 10 to the 14th hertz, and I want to find its energy in both joules and electron volts so I can compare the two, I'm simply going to take E equals hf for both cases. The only thing that's going to be different is which version of Planck's constant that I use. And in this first case, right here, I'm going to use the joules version of Planck's constant times the frequency to get that the energy of that photon is 3.98 times 10 to the negative 19 joules. So you can see it's really, really small. Now, if I do the same thing, except this time, find the energy in electron volts, again, the only difference is I use the electron volt version of Planck's constant, same frequency, I get an energy of 2.48 electron volts. And see, that's a more natural number. That's one that's scaled properly. So a lot of times we like to use electron volts when we're just talking about this, but joules is also our common use in use for energy, so we can use either one of them. Now, we can go the other direction. If I know the energy of the wave, I can also figure out its frequency. Same equation, except now since I know the electron volt energy in this case, that goes in for E, use the Planck's constant that goes with electron volts, and divide, I get a frequency of 7.24 times 10 to the 14th hertz. Now, those other equations that we've done with waves, like the wave equation, velocity equals wavelength times frequency, and their relationship between frequency and period, where they're the inverses of each other, those still apply because those are still proper wave equations that go along with this. So I can take that frequency and actually figure out the period of the wave by taking the inverse of that frequency, and I get 1.38 times 10 to the negative 15 seconds for the period. That means it takes that small amount of time for just one of these waves to pass. I just mentioned the wave equation. It turns out we can use this as well, but we usually rewrite it a little bit. Instead of V equals wavelength times frequency, a lot of times we use C. Lowercase c is the symbol we use for the speed of light. So in Einstein's equation E equals mc squared, c is the speed of light, 3 times 10 to the 8th meters per second. Since all electromagnetic waves travel the same speed, we just throw that in as our constant. So we get c equals wavelength times frequency. A couple of other things that's handy is a lot of times, since these numbers are so small, we come up with abbreviations so we don't have to use scientific notation as much. And the one that's most common today is nanometers, where in this example, 5 nanometers will be the same as 5 times 10 to the negative 9 meters, where nano simply means to the negative 9th power. One very old unit that we used to use is an angstrom, and its symbol was an A with a little circle on top, and it's 1 times 10 to the negative 10th. So 5,200 angstroms would be 5,200 times 10 to the negative 10th. And then we could turn that into more proper scientific notation, which will be 5.2 times 10 to the negative 7th meters. Commonly today, we don't use angstroms anymore. We just use nanometers. It just makes the metric system so much easier that way. So let's combine the wave equation and energy of a photon. So in this case, we got a wave that has a wavelength of 600 nanometers, and I want to find its energy in joules. So the first thing is, since I have a wavelength, I really need frequency. So I'm going to take our wave equation and the wavelength and find the frequency. So 3 times 10 to the 8th equals 600 times 10 to the negative 9th times frequency, divide, I get a frequency of 5 times 10 to the 14th hertz. Now that I know the frequency, I can put it in the energy equation there. And since I want the energy in joules, I want to use the joules version of Planck's constant and multiply those through, and I get an energy of 3.32 times 10 to the negative 19 joules. But again, the important thing is make sure you use the version of Planck's constant that goes with what you want the answer in. Now going backwards, we can go the other direction. Let's say I give you the energy, 12 electron volts, and I want the wavelength. Well, since I already know energy, I want to use the energy of a photon equation and figure out the frequency. And since it's in electron volts, I want to use the electron volt version of Planck's constant. And I get a frequency of 2.9 times 10 to the 15th hertz. Now that I got the frequency, I can put that in the wave equation with the speed of light and figure out that my wavelength is 1.03 times 10 to the negative 7 meters. Or if I want to actually put it in nanometers, it'll be 103 nanometers. And we can trade off different things and find different parts, but these are some of the basic equations that you will do. Thanks, and I'll talk to you later. Goodbye.